In the heart of Kentucky, amidst the smoke, corn, and oak barrels, Maker's Mark has been brewing its potent magic since 1953. 34 million bottles a year, made with respect for the recipe, family, fire, and time. They don't just pour whiskey here, they forge character in every drop, with corn, wheat, smoke, and fire. But how did it all begin 72 years ago? Or perhaps even earlier? The story of Maker's Mark is about a family that didn't compromise. About how one man and one woman decided enough of making bourbon that just burns in your throat. It's time to make something that has taste, smoothness, and a legend you can't mistake for anything else. It all started even before Maker's Mark, with the Samuels family, who had been making whiskey since the 1780s. It was a true bourbon dynasty, generation after generation, barrels, recipes, pot stills. But the bourbon they made was like most at the time, strong, woody, harsh, with the aftertaste of a smoky punch. Then, Bill Samuels Sr. came onto the scene, a man with character. In 1953, tired of traditions and the constraints of the old recipe, he took all his whiskey wisdom, acquired over generations, and burned it to hell in a furnace. Yes, he literally burned the old bourbon recipe to start with a clean slate. He needed something new, something different from the competitors. Without the harsh aftertaste of rye, without the sharp finish that hits you in the throat. And then an idea came. Replace the rye with soft red winter wheat. Less aggression, more roundness, body, warmth. It was revolutionary. While Bill experimented with the grain, Margie Samuels, his wife, held in her hands everything we now recognize as Maker's Mark. She came up with the name. Maker, one who creates. Mark, the craftsman's seal. She designed the signature label, which she wrote by hand, and decided it should be torn, as if from a workshop. And most importantly, she came up with that very red wax into which the neck of every bottle is dipped by hand. Red, hot, like a sealed kiss. She was a brand architect, marketer, and designer all in one bottle, long before those words became trendy. And Maker's Mark wouldn't be what it is without her. The distillery was opened in Loretto, Kentucky, where the water is soft and limestone filtered, perfect for bourbon. There, a red watermill still stands as a symbol of moving forward. The bourbon is aged in charred American oak barrels, as it should be, and is not chill filtered to not lose its flavor. The bottles are filled, hand-dipped in red wax, and each one is slightly different. Like a fingerprint. Maker's Mark wasn't in a hurry to go mainstream. They didn't run TV commercials. They didn't drop the price. They just made bourbon that people wanted to share with a friend. And so, from a small brand on a farm, Maker's Mark grew to 34 million bottles a year. And to this day, at the distillery, you can see that old recipe, not in a book, but in ashes. Bill Samuels destroyed the past to create a bourbon that isn't afraid of the future. If you've ever held a bottle of Maker's Mark in your hands, heavy, with red wax, rough lettering, and a light aroma of smoke, you've touched the very thing that goes through months of fire, fermentation, and wood. This bourbon isn't made on the fly, and is not poured into millions of bottles from a single tank. This is manual labor and old rules. Let's break it down one by one. The basis of any bourbon is grain. At Maker's Mark, it all starts with the right mix. 70% corn, which gives the body sweetness and weight. 16% soft red winter wheat. Unlike rye, it makes the profile smooth, without a harsh kick to the back of the throat, and 14% malted barley, which kicks off fermentation. No malt, no reaction, no whiskey, nothing to talk about. All these grains come from American farms, with which Makers has worked for years, for generations. Each batch is accepted not on faith, but through the laboratory and the nose. Moisture, size, smell. Everything is recorded. There's no "it'll do" here. Everything is under control, as on a shooting range. The grain arrives. It's ground in steel mills to a coarse, hard meal. Nothing like flour. This is a fighter's mash, ready for the fire. The ground grain is thrown into giant copper tanks. Soft limestone water from the depths of Kentucky is added, and the temperature is raised to 212 degrees Fahrenheit. All this steams, foams, breathes heavily. The mash is born. Starch begins to break down into sugars, which will later become the basis of alcohol. The air smells heavy, malty, with a hint of hot corn. The heat comes from within, like from a forge. When the mixture cools to the right level, it's pumped into fermentation tanks, and here begins a process that isn't visible from the outside. At Maker's Mark, they use the same yeast that the Samuels family had been keeping since the 1950s. They haven't changed the culture or the method. Fermentation lasts for several days in oak tanks. It's the oak that provides the microflora, breathes, and works together with the whiskey. Microorganisms chew up the sugar, exhaling alcohol and heat. Everything boils, bubbles, and smells so that your head spins. Ripe bananas, yeasty bread, a little acidity, a little hoppiness. This isn't just fermentation. It's a deep force that carries the mash forward. Then comes distillation. What separates the truth from the excess? Instead of trendy steel systems, good old copper pot stills, in which the spirit of the whiskey is cut through 2 distillations. The first distillation is rough, cloudy. The low wine has 25% alcohol. The second is clean, shiny. The high wine with a strength of over 130 proof. Here the future bourbon is born. Rich, oily, powerful. The copper removes sulfur, adds nobility to the body. Not cold, but alive. The whiskey at this stage already has a scent. Not of alcohol, but of what will become a drink. Wood, toasted bread, warmth. The distilled bourbon is still hot, still a bit of a hooligan. It's poured into freshly charred American oak barrels, each one made by hand from white oak. No glued panels, all from solid staves, dried for years in the open air. Then, fire. The inside of the barrel is burned with flames, not for beauty, but so the inner layers of the wood give the whiskey caramel, vanilla, and that same woody backbone for which it is recognized even blindfolded. Bourbon is poured into the barrel, golden, fragrant, strong, and the long aging begins. How many years? It's not counted in years here, it's counted by taste. On average, 6 to 7 years, but no batch is released until the master says, "This is it." All this time, the barrel stands in a warehouse where the heat in summer reaches 110 degrees Fahrenheit, and in winter, it can drop to 20. The wood expands and contracts, breathes, presses on the whiskey. Part of the liquid evaporates. The angels share, they say. Up to 10% disappears each year, seeping into the ceiling. But what remains becomes stronger, more complex, deeper. Here the smell of leather, caramel, dampness, and honey appears. The bourbon absorbs everything it needs from the wood, and nothing extra. When the time comes, batches from several barrels are blended by hand. More precisely, tasted, combined, checked. There's no one taste for all line here. There's a master with a palate like a detector. If the bourbon passes, it's bottled. If not, it waits longer. And so, when the bourbon is ready, it's poured into the signature thick bottles, each of which is checked beforehand for shine, weight, and shape. And then, the red wax. What you see from afar. What no one imitates. At Maker's Mark, they still dip each bottle by hand into hot red wax. The bottle goes in neck first to the middle, is lifted out, and the wax slowly drips down, leaving a thick, characteristic drop, like a seal. No two are alike. Each one is uniquely wild. And then, and only then, the bourbon goes into boxes, which are sent to bars, stores, and to people who appreciate not just alcohol, but work into which time, tradition, and character have been invested. The guys in work clothes, with calloused hands, glance at the steam clouds. Everything is going as it should. One pours the yeast, another checks the temperature in the fermenter. In the cooperage, a dry pop explodes. Another oak barrel has been charred inside. Nearby, a woman, focused and calm, dips bottles into hot wax. Her movement is precise. Not a single extra drip. For lunch, meat with bread, coffee from a thermos, and a short laugh. Did you see how Jim mixed up the barrels yesterday? Then again, barrels, spirit, wood, red wax, and so on, day after day. They don't rush. They're making bourbon.
Hold a 1-inch tungsten cube. It weighs nearly 1 pound, denser than gold, heavier than lead. Drop it and the floor dents, not the cube. This metal refuses to melt until 6,192 degrees, hotter than Earth's core beyond temperature where other metals vaporize. Light bulb filaments, armor-piercing bullets, rocket nozzles. Tungsten survives conditions that destroy everything else. Yet it starts as dull gray rock, looking worthless. How does brittle ore transform into metal that won't surrender? Why does one nation control 70% of global supply? Stay with us. You'll witness industrial-scale mining reshaping mountains and discover tungsten's shocking secret. This indestructible metal is so brittle in pure form it shatters like glass. The Dayu tungsten mine in Jiangxi, China dominates the landscape. An open pit 3 miles across descending 800 feet into earth. Giant haul trucks, each carrying 400 tons, crawl spiral roads looking like toys from rim's edge. This single mine produces 40,000 tons of tungsten concentrate annually, enough to manufacture 2 billion light bulbs. 70% of world's tungsten comes from Chinese operations like this. Watch the blast sequence. Drillers bore holes 50 feet deep in geometric patterns across the pit floor. Each hole gets packed with explosives, 200 pounds per hole, hundreds of holes per blast. The detonation ripples across the face in sequence, fracturing 10,000 tons of rock in 30 seconds. Dust clouds billow 300 feet high, visible from orbit. What took nature millions of years to create, humans demolish in half a minute. The ore, wolframite and scheelite, contains just 0.5% tungsten. That means 99.5% is waste requiring removal. Massive crushers reduce boulders to gravel. Ball mills grind further. Rotating drums containing steel balls pulverize ore to powder finer than flour. The grinding noise is deafening, continuous thunder as metal crushes rock. Separation uses gravity and magnetism. Wolframite, being dense and magnetic, concentrates easily. Scheelite requires froth flotation. Chemicals make tungsten minerals hydrophobic, clinging to bubbles while waste sinks. The concentrate, now 15% tungsten, ships to processing plants. China's dominance isn't accidental. They control reserves, processing knowledge, and critically tolerate environmental damage Western nations won't accept. Tailings ponds stretch miles, filled with chemical-laced sludge that'll remain toxic for centuries. Processing concentrate into pure tungsten trioxide requires acid digestion. The concentrate gets dissolved in hydrochloric or nitric acid, violent chemical attack breaking molecular bonds. Tungsten dissolves while impurities precipitate out. The solution, now containing tungsten compounds, undergoes pH adjustment causing yellow tungsten trioxide powder to crystallize. This powder undergoes hydrogen reduction, the crucial transformation. Inside tube furnaces heated to 1,800 degrees, hydrogen gas flows over tungsten trioxide. The hydrogen strips oxygen atoms, leaving metallic tungsten powder. But here's the challenge. Pure tungsten powder is useless. The particles don't bond. Press them together and they crumble. Tungsten's ultra-high melting point makes conventional melting impossible. No crucible survives temperatures required. The solution? Powder metallurgy. Powder metallurgy bypasses melting through sintering. Particles fuse below melting point under pressure and heat. Tungsten powder gets pressed into desired shapes using hydraulic presses, generating 50,000 psi. The compacts, called green bodies, are fragile, handle roughly, and they disintegrate. The green bodies enter sintering furnaces operating at 4,500 degrees in hydrogen atmosphere. At these temperatures, tungsten atoms migrate across particle surfaces, welding together without liquefying. The process takes 12 hours. What emerges has transformed The powder compact becomes solid metal with 99% density. Dimensional changes are predictable but significant. Parts shrink 18% during sintering. Engineers must design oversized greens compensating for this shrinkage. Pure tungsten remains problematic. It's brittle at room temperature, difficult to machine. The solution? Alloying. Adding 2% thorium or lanthanum dramatically improves workability. These elements prevent grain growth during sintering, creating fine-grained structure that machines more easily. The most common tungsten product worldwide is tungsten carbide, tungsten powder mixed with carbon, sintered together. Tungsten carbide achieves hardness second only to diamond. Cutting tools made from tungsten carbide last 10 times longer than steel equivalents. Mining drill bits, machining inserts, industrial dies. Anywhere extreme wear occurs, tungsten carbide dominates. The material cuts steel like butter but shatters under impact. Drop tungsten carbide block on concrete and it explodes into fragments. The combination of extreme hardness and extreme brittleness defines tungsten's paradox. Wire drawing demonstrates tungsten's remarkable properties. The sintered tungsten gets heated to 3,000 degrees and drawn through progressively smaller diamond dies. The wire diameter reduces from 1/4 inch to thousandths of an inch, thinner than human hair for light bulb filaments. This drawing process work hardens tungsten, increasing strength. Modern LED lights made tungsten obsolete for household illumination, but specialty applications remain. Electron microscopes, X-ray tubes, high-temperature furnace elements. Anywhere electricity must flow through extreme heat, tungsten wire delivers. The element's resistance increases with temperature, making it self-regulating. In light bulbs, hot filament resists current flow, limiting power draw and preventing burnout from voltage spikes. That wire glowing white-hot at 6,000 degrees, tungsten operating at 70% of its melting point, yet lasting thousands of hours. Military applications drive demand relentlessly. Tungsten's density, 19.3 grams per cubic centimeter, nearly identical to gold, makes it ideal for kinetic penetrators. Armor-piercing ammunition uses tungsten or tungsten alloy cores. Fired from tank cannons at 5,000 feet per second, these projectiles punch through steel armor through sheer mass and velocity, not explosive force. The ethical controversy is intense. Depleted uranium performs similarly but raises radioactivity concerns. Tungsten offers equivalent performance without radiation, but mining's environmental cost is staggering. Each ton of tungsten requires processing 200 tons of ore, generating mountains of toxic waste. The metal that survives Earth's most extreme conditions is extracted through processes poisoning the planet. Swedish chemist Carl Scheele identified tungsten oxide in 1781, studying the mineral scheelite. Spanish brothers Juan and Fausto El Huyar isolated metallic tungsten 2 years later. The name derives from Swedish tungsten, heavy stone. For a century, tungsten remained laboratory curiosity. Everything changed when Thomas Edison needed light bulb filaments in 1879. He initially used carbon, which burned out quickly. By 1904, manufacturers switched to tungsten, revolutionizing electric lighting. World War I revealed tungsten's military value. High-speed steel cutting tools containing tungsten enabled mass production of weapons. Today's annual production exceeds 90,000 tons, with China dominating supply chains so completely that Western nations consider tungsten a strategic vulnerability. Carbon emissions remain problematic as tungsten production generates 8 tons of CO2 per ton of metal, primarily from energy-intensive processing. Recycling exists but remains limited. Only 30% of tungsten gets recycled, far below rates for aluminum or steel. Here's the secret we promised. Tungsten's incredible strength comes from its weakness. Pure tungsten is brittle, shattering easily. But that brittleness stems from its crystal structure. Atoms packed so tightly that dislocation movement, the mechanism allowing metals to deform, essentially stops. This atomic rigidity creates the highest melting point, extreme hardness, and resistance to deformation. The metal survives temperatures melting steel because its atoms simply refuse to move. Adding trace elements creates enough flexibility for workability while maintaining strength. From Chinese mountains to cutting edges worldwide, the transformation completes. we've mastered metal that defies conventional metallurgy, processing it through techniques developed when melting proved impossible. That drill bit cutting through rock, that filament glowing white hot, that bullet-piercing armor, all share tungsten's fundamental contradiction. The strongest metal is also the most fragile. The element that won't melt is useless without powder metallurgy. We've learned to work with nature's extremes by accepting, not fighting, inherent limitations. Tungsten doesn't compromise. Neither do the engineers who've learned to shape it.
Every year, over 40 million new gadgets hit the market, but almost nobody knows about the metal that makes them actually work. Why can a tiny element buried deep underground literally launch an entire civilization, from the Bronze Age to modern electronics? And what do ancient swords, tin cans, and your smartphone have in common? In this video, we're uncovering the secret of tin, the metal that built the past, runs the present, and hides a fact you've definitely never heard before. Stick around until the end. That's where the real mystery reveals itself. Tin isn't just some new trend. This is a metal with a deep-rooted history spanning thousands of years. Its discovery sparked a genuine revolution that forever transformed the course of human civilization, launching what we call the Bronze Age. Picture this. Ancient craftsmen learned to extract copper and forge tools from it. But copper was soft. Then, whether by accident or experimentation, they discovered something remarkable. If you added a little bit of another then unknown metal to molten copper, tin, the alloy became incredibly strong, hard, easier to cast, and held a sharper edge. That metal was tin. The copper-tin alloy became known as bronze. Bronze swords, shields, tools, jewelry, all of this suddenly became accessible, giving ancient civilizations a massive advantage. It was a true technological leap that transformed warfare, agriculture, and art. Tin became so valuable that real battles were fought over its deposits, and trade routes to tin mines, like those in Cornwall, Britain, were incredibly important. Over the centuries, tin stayed valuable. It was used as a coating for other metals to protect them from corrosion. For example, tin plate, a thin sheet of steel coated with tin, which was used to make cans. It was also used to make soft solders that joined metals together, and in the production of mirrors, and even to create organ pipes and coins. But its true renaissance came in the 20th century with the rise of electronics. Over 50% of all global tin consumption goes to this industry. Solder. That's its main job. Your computer, smartphone, TV, inside them, thousands of electrical components are connected together. These connections are made using solder, which is usually an alloy of tin with other metals, like lead in the past, now mostly with copper, silver, or nickel. Tin is perfect for solder because it has a relatively low melting point, which makes it easy to melt and form connections without damaging sensitive electronic components. Tin also wets metals, meaning it easily flows across the surface, creating a strong electrical and mechanical bond. It's got great electrical conductivity too, and it's corrosion resistant. Modern electronics use what's called lead-free solder, which is a huge step forward for the environment. Tin is the main component in these alloys. Without reliable soldered connections, the entire complex architecture of microchips would simply fall apart, and your gadget would turn into a pile of useless parts. Tin is used to coat other metals, especially copper, on printed circuit boards. This protects the copper traces from oxidation and makes the soldering process easier. It's also used to coat connectors, which improves their electrical conductivity and corrosion resistance. Tin isn't a super common element in the Earth's crust. Its primary mineral is cassiterite, basically tin oxide. It's a pretty dense mineral that's often found in placer deposits, meaning you can extract it from river sediments or ancient coastlines. Over 70% of the world's tin production is concentrated in 4 countries across Southeast Asia and South America: China, Indonesia, Myanmar, and Peru. This makes the tin market highly sensitive to political and economic events in these regions. Tin mining begins with the exploration phase. Geologists, armed with modern technology, conduct surveys, drilling, and analysis of soil and rock samples to find locations where cassiterite concentrations are high enough for economically viable extraction. Once a deposit is identified, development begins, which can follow two main paths depending on the type of deposit. The first and most common method of tin mining is from placer deposits. Picture this. Over millions of years, cassiterite washed from bedrock by water and erosion accumulated in riverbeds, at the bottom of lakes, or on ancient seashores.
It settled like sand in what's called placer deposits. Extracting from these deposits is often way simpler than digging underground mines. Here, they use massive dredges, floating factories that scoop up tons of soil and gravel from the bottom of waterways, or they deploy hydraulic monitors, powerful jets of water under high pressure that blast away soil from riverbanks or hillsides containing cassiterite. The blasted rock then flows to primary processing, where gravity methods, exploiting density differences, separate the cassiterite from lighter waste rock. Think industrial-scale gold panning, only gigantic. The second method? Extracting from primary deposits, where cassiterite sits directly in solid rock. That's where traditional underground mines come in, same as mining any other metal. Miners drill tunnels and boreholes into the rock, use explosives to blast apart the ore vein, then loaders collect the ore and haul it to the surface. It's a more expensive and complex operation, requiring heavy-duty equipment and strict safety protocols. Once extracted, the ore, no matter where it came from, heads to a processing plant. First, it's crushed and ground into a very fine powder in mills to free the cassiterite crystals from the surrounding rock. Then various enrichment methods kick in. The first method, gravity separation. Since cassiterite is a pretty dense mineral, it gets separated from lighter minerals using water. This can happen in jigs, concentration tables, or spiral separators.
The second method is flotation. Sometimes, for further enrichment or to separate cassiterite from other minerals, flotation is used, where cassiterite selectively sticks to air bubbles and rises to the surface as foam. As a result of all these processes, a tin concentrate is obtained that already contains more than 50% cassiterite, or even more. This concentrate then goes to a metallurgical plant to produce pure metallic tin. Here, the concentrate, which is tin oxide, is mixed with coal, which acts as a reducing agent, and fluxes. Fluxes are substances that help separate impurities. This mixture is heated in special furnaces to high temperatures, typically around 2400 degrees Fahrenheit. At these temperatures, the carbon steals the oxygen from the tin oxide, releasing pure metallic tin, which melts and flows to the bottom of the furnace.
The molten crude tin still contains impurities from other metals, so it goes through another crucial stage, refining. This can be thermopurification, where the lead is heated to specific temperatures so other metals separate out or float to the surface. Or more often, electrolytic refining, which allows for extremely high tin purity. High purity means almost 100% in this case. Can you believe that? This is critically important, especially for the electronics industry, where even the tiniest impurities can affect conductivity and component reliability.
More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel, 2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization. The Lebedensky Quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock. The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter. 30 stories of pure metal and fire. Lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake, several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights. First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1,800 degrees, ore becomes spongy iron. At 2,700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2,700 degrees Fahrenheit. It glows blindingly white with an orange tint. Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle: manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are two methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red, surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls. Steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls, even thinner, dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere. Temperature drops to 1,400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel, the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone. 95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips. Iron and steel are civilization's skeleton. Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world. And so, traveling from explosions and 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year. 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together.
Every year, the world melts over 1 billion tons of pig iron. But where does all that fiery metal come from? Imagine a giant furnace as tall as a 35-story skyscraper that never sleeps. Its guts glow like the Earth's core, and the temperature hits 3,600 degrees Fahrenheit. That's 2,000 Celsius. This is a blast furnace. They don't just melt metal here. They give birth to the heart of industry. But there's a secret that only the guys standing at the tap hole know. If you stick around to the end, you'll find out what's really happening in the center of this burning fortress, and why it changes everything. Imagine a colossal tower, taller than a 35-story skyscraper. The ground beneath your feet vibrates slightly from its relentless work, and the air is filled with a hum, like the breathing of a giant beast. At night, its top glows, pushing back the darkness. This is a blast furnace, a massive vertical smelter, where 24 hours a day, 7 days a week, the magic of turning ore into metal happens non-stop. Why blast furnace? The name comes from the process itself, and it's no accident. The whole secret to a blast furnace is the constant blast of incredibly hot air that fuels the fire and kicks off all the necessary reactions. If you were to slice a blast furnace open, you'd see it looks like a stretched out bottle. Every part of it has a name and a purpose. The walls of the furnace are lined with special refractory bricks, capable of withstanding temperatures that would melt solid rock. This is a true fortress, built to tame fire itself. So what do they feed into this fiery throat? The process is like cooking from a very strict recipe. The mix of ingredients loaded into the furnace is called the charge. Here are its main components: iron ore, fuel, coke, and fluxes. These 3 ingredients are loaded into the furnace in precisely measured layers. A layer of coke, then a layer of ore with fluxes, then coke again, and so on. Every few minutes, a new batch weighing tens of tons is sent into the furnace. The iron ore is the foundation of it all. They usually don't just use raw ore dug from the ground, but specially prepared sinter or pellets. These are baked clumps of fine ore, or rolled balls of ore concentrate. The main goal is to have as much iron oxide in the raw material as possible, from which the oxygen will later be ripped out. Coke is coal that's been cooked in special ovens without access to air. After this treatment, it becomes strong, porous, and burns with an immense amount of heat. But that's not its only role. The carbon that makes up coke is the real magician that turns ore into metal. The flux is most often ordinary limestone. Why is it needed? The ore and coke always have useless impurities, so-called gangue. The limestone helps to bind these impurities, forming an easily meltable slag. So, the charge is loaded. What's next? This is where it gets interesting. Two streams move towards each other. From the top, the layers of the charge slowly descend, and from the bottom, a hurricane of superheated gases rushes up to meet them. It all starts at the bottom, in the hearth. Through special pipes called tuyères, air heated to a scorching 2,200 degrees Fahrenheit, 1 to 200 Celsius, is blasted into the furnace under huge pressure. That's hotter than volcanic lava. Meeting the red-hot coke, the oxygen in the air instantly ignites. The temperature in this zone skyrockets to 3,600 degrees Fahrenheit, 2,000 Celsius. This creates carbon dioxide. But as it rises higher and passes through new layers of coke, it turns into another gas, carbon monoxide. And this gas is the real oxygen thief. As this searing hot stream of gas rises up the furnace shaft, it envelops the chunks of ore and begins to greedily rip the oxygen from them, leaving behind reduced, spongy iron. The reduced iron continues its journey downward into hotter and hotter zones. It passes through the glowing layers of coke and, like a sponge, begins to soak up its carbon. And here's where something amazing happens. Pure iron melts at a very high temperature of 2,800 degrees, 1,530 Celsius. But soaking up carbon dramatically lowers that melting point. That's why a blast furnace doesn't produce pure iron, but an alloy of iron and carbon, pig iron, which becomes liquid at just 2,200 degrees, 1/200 Celsius. Roughly every 40 to 60 minutes, enough liquid products have collected in the bottom of the furnace. It's time for the climax, a truly mesmerizing sight. A furnace worker, the keeper, uses a special drill to punch open a hole in the furnace wall, the tap hole. First, they tap the slag. It's lighter than the iron, so it floats on top. It's a molten, lava-like mass that flows into special ladles. And then they open the iron tap hole, and a dazzling, sparking stream of molten metal erupts with a roar. This is the River of Fire. The temperature of this stream is around 2,700 degrees Fahrenheit, 1,500 Celsius. It flows down special troughs, bathing everything around in a blinding light, and fills giant ladles that look like railway tankers. Each of these ladles holds hundreds of tons of liquid metal. From here, the pig iron will be sent to its next stage, either poured into molds, or, more often, sent for further processing into steel. A blast furnace is an amazing operation that produces more than just pig iron. The byproducts are just as important. The blast furnace slag, which we've already mentioned, becomes a valuable raw material for making cement, building blocks, and road aggregate after it's cooled and crushed. The blast furnace gas that comes out of the furnace isn't just released into the atmosphere. It's cleaned of dust and used as fuel to heat the very same air that's blasted back into the furnace. It's a closed-loop system that makes the process more economical. Without a doubt, metallurgy is a serious challenge for the environment. However, modern technologies are constantly evolving. When blast furnaces are modernized, powerful filters and cleaning systems are installed to capture dust and harmful gases. Scientists and engineers around the world are working on creating green technologies, like using hydrogen instead of coke, to make metal production cleaner. But for now, the blast furnace remains the king of metallurgy. And every time you see a bridge, a skyscraper, or a train, remember these fiery giants and the people who tame rivers of fire to give the world a strong and reliable foundation. For 75 years, from the late 19th century to the 1970s, the USA was the undisputed world leader in the production of pig iron, steel, and rolled products. During this period, the American iron and steel industry wasn't just a sector of the economy, it was the key or barometer of the American economy. In the 1920s, for example, the country produced about half of the world's pig iron. Imagine that. Every other ton of this strategic metal in the world was born right here in American furnaces. Every year, the world produces over 130 million tons of glass. But few people know that behind every clear window, bottle, or skyscraper facade lies a true symphony of fire, air, and light. Imagine a river of molten sand flowing over a mirror of tin, giving birth to perfectly flat sheets of glass so smooth they can reflect the clouds. But there's another kind of glass, one that's alive, with a soul, created by the breath of a craftsman and the fire of a furnace. Stick around to the end, and you'll see how ordinary sand travels through a 3,000-degree journey to become the transparent marvel our world is made of. While the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in the methods that give it character and uniqueness. This journey from a simple, transparent sheet to a work of decorative art is a fascinating one. To create glass with individuality that carries the mark of a human touch, craftsmen still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at 2,000 degrees Fahrenheit. He gathers a honey-like ball of glowing glass on the end of the pipe and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, shining hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach several feet in length. After the ends of the cylinder are cut off, it's sliced lengthwise and placed back in the furnace. There, under the heat, it slowly unrolls like a scroll, and the craftsmen smooth it into a flat sheet. Glass born this way is never perfectly flat. It's alive, retaining subtle waves, tiny air bubbles, and fine lines that tell the story of its fiery birth. This glass has a watery, organic quality that can't be replicated by a machine. But the creation of unique glass doesn't stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing allows artists to literally paint with glass. Different colored pieces of glass are arranged on a base sheet and sent into a kiln, where at 1,500 degrees Fahrenheit, they melt together into a single piece, creating bright, painting-like compositions. Closely related is the process of slumping, or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold placed beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two layers of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating intricate patterns on its surface, from simple geometric shapes to photorealistic images. In this way, by combining ancient crafts with cutting-edge technology, modern production transforms simple glass into an expressive architectural material capable of shaping light, color, and space. In today's world, where tons of used glass containers are collected daily, the journey from the recycling bin to a new bottle isn't just remelting. It's a high-tech odyssey driven by computers and light. Imagine a mountain of crushed glass, dozens of feet high, where clear, green, and brown shards are mixed with labels, caps, and ceramic contaminants. Turning this chaos into pure raw material is a job for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, like a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull out any steel contaminants, and then eddy current systems literally shoot aluminum caps and foil into separate containers. Powerful blasts of air blow away light paper labels and plastic residue. But the hardest task is yet to come. Removing impurities that are almost identical to glass in weight and size, like pieces of ceramic, stone, or porcelain. These enemies of glass don't melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to high speed and fly through a scanning zone. For a split second, each fragment is illuminated by a bright light, and high-speed cameras take hundreds of pictures. A computer system, with lightning speed, analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and commands a battery of air jets. A precise, sniper-like puff of compressed air knocks the unwanted element out of the mainstream, sending it to waste. This process is repeated thousands of times a minute. At the same time, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only clear glass, knocking out all colored fragments with air jets, or separate the stream into 3 distinct color fractions. The result is a perfectly clean, color-sorted raw material. Cullet, ready for a new life without any loss of quality, which is the pinnacle of the modern circular economy. This raw material can then be used to make flat glass. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that turns ordinary raw materials into perfectly transparent sheets. It all begins in a massive melting furnace, the fiery heart of the plant that runs continuously for years. Into this furnace, which resembles a lake of molten fire, a carefully measured mix, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stability. A significant amount of cullet, or crushed recycled glass, is added to this to help speed up the melting process. Inside the furnace, at hellish temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a uniform, viscous liquid. The melting process is strictly controlled to ensure all particles are completely dissolved and gas bubbles are removed, creating a flawlessly pure melt. From the furnace, this stream of glowing orange molten glass, resembling a river of lava, flows smoothly into a bath of molten tin. This is the culmination of the process known as the float process. The tin bath, stretching for hundreds of feet, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and doesn't mix with it, it spreads out over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from the bottom, and surface tension smooths it from the top, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with pinpoint accuracy. After forming a perfectly flat surface, the glass ribbon, still very hot but now solid enough to hold its shape, enters the calmest but most critical stage, annealing. It enters a long tunnel known as an annealing layer. If glass is cooled too quickly, its surface will contract faster than its interior, leading to massive internal stresses that will make it brittle and prone to shattering. In the layer, however, the glass temperature is slowly and controllably reduced over several hundred feet, from over 1,000 degrees down to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of perfectly transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Imagine a metal that's lighter than steel, stronger than aluminium, and can withstand temperatures at which other materials simply burn up. A metal used to build aircraft that conquer space and implants that serve people for a lifetime. Sounds like science fiction? But this is titanium, one of the most mysterious metals on Earth. It starts with tiny grains of ilmenite and rutile and ends up as parts for supersonic jets and spacecraft. But few people know. Behind the gleam of titanium lies a manufacturing secret so dangerous and energy-intensive that it's rarely spoken of. If you watch till the end, you'll learn something that will forever change your perception of this metal. The story of titanium production begins in the late 18th century when, in 1791, a British clergyman and amateur mineralogist named William Gregor discovered a new metal in the mineral ilmenite, which is now the main source of titanium. Initially, this metal was called menaconite, but later, in 1795, the German chemist Martin Klaproth rediscovered the element in the mineral rutile and named it titanium, in honor of the mythical Titans, giants of ancient Greek mythology. However, the pure metal was first successfully isolated only in 1825 by the Swedish chemist Berzelius, though at that time it was contaminated with impurities and practically unsuitable for industrial use. The first attempts at industrial production of titanium began only in the 20th century. In 1910, the American chemist Matthew Hunter obtained a small amount of pure titanium, and the real breakthrough came in 1925 when Dutch scientists Van Arkel and de Boer developed a method for producing high-purity titanium, paving the way for its widespread application. From the mid-20th century, titanium production developed intensively, especially in the USA, where the metal became indispensable in aviation, the space industry, and military applications. The production of titanium starts with the mining of titanium-bearing raw materials, mainly the minerals ilmenite and rutile, which contain titanium oxides. These ores are found in placer or lode deposits and are widespread across the globe, particularly in Australia, Canada, China, Norway, and South Africa. After mining, the ore undergoes a complex multi-stage processing. First, it is enriched, separating the titanium minerals from the waste rock to obtain ilmenite or rutile concentrates. Then, the concentrates are subjected to chlorination, which results in the formation of titanium tetrachloride, a volatile substance that is purified by distillation. This process allows for the removal of impurities and the production of a high-purity intermediate product. Next, the titanium tetrachloride is reduced with magnesium or sodium in special reactors at high temperatures in an inert atmosphere, producing titanium sponge, a porous metallic powder. This titanium sponge is then pressed, melted, and cast to obtain ingots or billets for further processing. The production of titanium is energy-intensive and expensive due to the complexity of the technological processes and the need to work in high-purity conditions. The main industrial method for producing titanium is the Kroll process, which remains the global standard. It involves the chlorination of titanium ore, purification of titanium tetrachloride, and its reduction with a metal, allowing for the production of high-quality metal for aviation, space technology, medicine, and other industries. Thus, titanium production begins with the mining of ilmenite and rutile, goes through complex chemical reactions and physical processing to transform natural minerals into a high-tech metal that combines lightness, strength, and corrosion resistance. The initial stages of titanium production are based on a complex, multi-step technological process that begins with the extraction and preparation of titanium-bearing raw materials, mainly ilmenite and rutile. These minerals contain titanium oxides, which must be converted into chemically pure titanium tetrachloride. To do this, the titanium ore concentrates are chlorinated in fluidized bed reactors at a temperature of 1,800 degrees Fahrenheit, where carbon and chlorine gas react with the raw material to form titanium and carbon monoxide. This tetrachloride contains impurities of other metals, which are removed by distillation to obtain high-purity technical titanium. The next key stage is the reduction of titanium tetrachloride to metallic titanium. The most common industrial method is the Kroll process, in which titanium tetrachloride reacts with magnesium in a vacuum chamber at high temperature. The result is titanium sponge, a porous metallic powder containing impurities of magnesium and magnesium chlorides. This reaction mass is subjected to vacuum distillation to remove impurities, after which the titanium sponge is pressed and remelted into solid ingots or slabs. The resulting titanium ingots are then used to produce alloys, rolled products, sheets, and complex parts. The entire process requires strict control of purity, temperature regimes, and safety, as titanium actively reacts with oxygen and nitrogen when heated. Just look at how incredible it is. A porous, light, and seemingly fluffy mass of metal. This is titanium sponge. It looks nothing like a regular metal bar, but more like a piece of metallic sponge or foam, only made of titanium. But this fluffy material is the first step towards creating strong and reliable titanium ingots, which are then used in aviation, medicine, and other high-tech industries. First and foremost, titanium ingots can be used to create titanium alloys, mixtures of titanium with other metals that enhance its properties. To obtain an alloy, alloying elements are added to the molten titanium, most often aluminium, vanadium, molybdenum, iron, or niobium. These additives change the metal's structure, increasing its strength, heat resistance, corrosion resistance, and improving its workability. The production of alloys usually takes place in vacuum arc furnaces, where the metal is melted at high temperatures in a protective atmosphere to avoid oxidation. To achieve a homogeneous composition, the alloy is remelted several times, after which it is cooled and prepared for further processing. The next stage is rolling. Ingots or slabs of titanium and titanium alloys are heated to a certain temperature to make the metal more malleable and are passed through special rollers. Rolling allows for reducing the metal's thickness, giving it the desired shape and size, as well as improving its structure and mechanical properties. The result is various types of rolled products: strips, ribbons, wire, and bars. Rolling can be hot or cold, depending on the requirements for the final product. From these rolled products, sheet metal is made: thin, flat blanks that are widely used in construction, aviation, medicine, and other industries. Titanium sheets are distinguished by their high strength and corrosion resistance, and are also easily subjected to further processing, cutting, bending, and stamping. The production of sheets requires precise control of thickness and surface quality, so after rolling, they are often subjected to additional processing, such as polishing or anodizing. To create complex parts, various methods of processing titanium and its alloys are used. These can include mechanical milling, turning, grinding, as well as modern technologies such as additive manufacturing using laser powder bed fusion. Additive technologies allow for the creation of parts with complex geometries that are impossible to produce with traditional methods. This is especially important for the aviation and medical industries, where lightweight, strong, and precise components are required. Furthermore, to enhance their performance characteristics, titanium products can undergo heat treatment, annealing, quenching, or aging. These processes change the internal structure of the metal, improving its strength, hardness, and fatigue resistance. In aviation, titanium is used for 15% of the weight of a modern passenger aircraft, significantly reducing its overall weight and increasing fuel efficiency. In the medical field, About 70% of implants, such as artificial joints and dental prostheses, are made from titanium or its alloys due to their biocompatibility and durability.